Welcome back everyone. In this lecture we will continue with the character theory. So, we want to prove some basic results about the characters of the representations. So, let us begin with this following proposition. As I said, we will actually just work with the modules where the characters make sense. So, we do not really put the assumption that we are working with the finite dimensional representations. So, if you are not comfortable, you can actually simply work with the finite dimensional representations. So, let us start with the G module. So, let us fix the notation G to be SLN plus 1. So, we have let us say V is a G module. Let us say it admits H character. Okay. Suppose this is given, let us say. So, then if we take any submodule of V, so for any submodule U of V, we have the character of U again lies inside R. Not only that, the character of V modulo U, the quotient also lies inside R. Moreover, the character of V is indeed given by the character of U plus the character of V mod U. Okay. This is the most important identity. So, basically if you think in terms of the exact sequence, the character actually respects that exact sequence very well. So, you have this exact sequence U to V, V modulo U to 0. So, this is the short exact sequence of modules we are considering, short exact sequence of G modules. So, when you apply character, then the character of the middle is indeed sum of the character on the ends. So, the character of the middle is nothing but the sum of the character of the end. Okay. So, once of course, you prove it for the length 2 short exact sequence, then you can actually extend this to any long exact sequence. Okay. I will leave that as exercise. So, the exercise is being, so if you have this long exact sequence, so then we will have this alternating sum of things. Okay. Let us say we have U1 etc. UK being G modules and all of them admit characters, all of them admit characters. So, that means, so the character of all these modules, they are all elements of our ring, character ring, okay, character of UI, they are all inside R for I range from 1 to k. So, if this is the case, then what happens? So, let us say let we have this, okay, suppose we have the following exact sequence, we have the following exact sequence of G modules. So, something like this, U1 is containing U2, containing U3, arrow UK to 0. So, then we can talk about the alternating sum of the characters here, because all this is exact sequence. Okay. So, then you go summation. So, let us actually see how we are writing this in this alternating sum. So, if you think about it, okay, the character of U minus the character of V plus the character of V modulo U. So, this is indeed 0, this is what we are writing. But if you want to actually keep the odd and even in place. So, this is first place, this is second place, this is the third place. So, then this is indeed written as, so minus 1 power I plus 1 u I summation I range from 1 to 3 equal to 0, where u 1 being u, u 2 being v, and then u 3 being v modulo u. Okay. So, that is how we have to interpret. So, if you interpret that way, then you can see that if you take this long exact sequence, then minus 1 power I plus 1 u I range from 1 to k, the character of this, the character sum should be 0. Okay. So, this indeed actually follows from what we have here in this length 2 exact sequence. Okay. So, this is something I will prove, and then you can prove this exercise on your board. Indeed, what do you need to prove? Okay, in actually proving both are equivalent, maybe let us actually talk about the long exact sequence itself. So, if you take this summation minus 1 power I plus 1 character u I equal to 0. So, proving this is same as proving that if you evaluate on any mu, that should be 0. Okay. So, this is equivalent to saying this minus 1 power I plus 1 character of u I evaluated at mu for I range from 1 to k. So, this is supposed to be 0, but this is equivalent to, so this is should be 0 for all mu in h star, but this is same as saying that summation minus 1 power I plus 1 u I of mu is 0, where I range from 1 to k, and this is true for all mu in h star. So, if you look at the muth weight spaces, the alternating sum, that should be 0, of course, the dimension of these things. Okay. But now, if you think about it, so this is what happens here. If you take this long exact sequence, if you have this long exact sequence of G modules, then of course, this is also long exact sequence as H modules. Then in particularly, I can look at the muth weight spaces. Okay. So, then it is easy to prove even at the muth weight space level, we have this long exact sequence. Okay. And this actually implies immediately summation minus 1 power I plus 1, the dimension of u I of mu is equal to 0 for I equal to k. Okay. So, this is something immediate. In the 2 case, again one can easily see, again this is inbuilt in the exercise. Okay. So, if you have a, let us say this simplest long exact sequence. Okay. So, then you can easily see that u again can be written as direct sum of u intersection v lambda, lambda comes from h star. Okay. Suppose v is written as direct sum of v lambda, lambda and h star. So, that implies that this is, maybe this you can take it as exercise. Now, with this you can easily see that v modulo mu again is written as direct sum of v lambda modulo u intersection v lambda, lambda in h star. So, in particularly you have this exact sequence at the level of lambda weight space, where u lambda is being u intersection v lambda. Okay. So, since this is what happens here, so dimension of v lambda becomes equal to dimension of u lambda plus dimension of v lambda modulo u lambda. So, this just follows from the dimension curve. So, this is not very hard to prove because this is all happening at the level of vector spaces. Okay. So, if you take the muth weight space, then it will just add up, there is no issue. So, now let us look at the character of the tensor products. Okay. Again we can make such statement. Okay. Let us say V and U being G modules, such that the character of V and character of U both are inside your character ring. So, now in this case we have the character of the tensor, again tensor over the complex numbers. So, this is going to be the product of the characters. So, the character of V times character of U. So, this is what happens for the tensor product. So, note that so what is the character of this V tensor U? Okay, let us actually rewrite everything in terms of the characters. The character of V by definition is summation V lambda e power lambda, where lambda runs over H star. Similarly, the character of U is going to be summation U mu e power mu, mu runs over H star. So, now what will be the product? The product character of V times character U. So, this is going to be summation. So, I am not writing the dimensions. So, the dimensions should be always written. So, this is going to be e power, let us say gamma, the product again you run it over summation dimension V lambda times dimension U mu, where lambda plus mu should be equal to gamma, where gamma runs over H star. So, this is going to be the e power gamma coefficient inside the product of the character. So, if you want to prove this is indeed true, so it is enough to prove that if you look at the gamma weight space, then the numbers matches or the coefficients matches on the both side. Okay. So, that means to prove that, so to prove character V tensor U is same as character V times character U, it is enough to prove so look at this V tensor mu, the gamma weight space. So, then that dimension, so you need to prove the dimension of this is same as summation dimension V lambda times dimension U mu, where lambda plus mu equal to gamma. So, this is what we need to prove. Okay. And this again will follow from the following direct sum. Okay. So, we indeed actually write it. So, if I take V tensor mu gamma, okay. So, this is not very hard to see. Okay. So, this is going to be span of all V tensor W, where V will come from V lambda and then W will come from U mu, such that lambda plus mu equal to gamma. Okay. So, that just follows from the following simple computation on the tensor product. If I compute H tensor V tensor W on the simple tensor, you can see that this is nothing but HV tensor W plus V tensor HW. Now, HV is going to be lambda of HV, because V is coming from V lambda, and then HW is going to be mu of HW, because W is coming from U mu. So, in particular if you put them together, you can see that this is going to be lambda of H V tensor W plus mu of H V tensor W. So, if you just take it out, this is lambda plus mu of H V tensor W. So, this is the computation that we have. Now, since V is direct sum of V lambda and U is a direct sum of U mu, if you choose a basis of V that comes from the basis of the weight spaces V lambdas, similarly you choose the basis of U which comes from the basis of U mu's. So, then the tensor product of that will give you basis of your V tensor W, sorry V tensor U. So, in particularly if you look at the gamma weight space, so that is going to be just a span of all these tensors. Okay. So, indeed if you write it in terms of the tensor, the gamma space is summation V lambda tensor U mu, where lambda plus mu equal to gamma. So, this is what we get it in terms of this. So, that proves that the dimension of this gamma weight space is just a sum of the dimension, because if you take the basis of V and basis of U, then we will be able to get the basis of V tensor U by taking the tensor product of the corresponding basis elements. So, that says that the character of V tensor U is nothing but the character of V times character of U. So, this is somewhat very important. Okay. So, this actually kind of covers more or less the important things I wanted to say about the characters. Okay. So, I will leave it to you to check, because in the finite dimensional case we also have the dual. So, if you take the dual, then what will be the character of so if we know the character of V, so in terms of the character of V, what will be the character of its dual? So, that is something you should actually think about it. Okay. So, to answer that question, first you need to answer that question for let us say finite dimensional irreducible modules. Okay. So, exercise, think about the character of V lambda star in terms of character of V lambda. Okay. So, it is going to be indeed, so you have to just take the corresponding inverses. Okay, I will leave it to you to think about it, it is not that hard. Note that if V lambda is finite dimensional irreducible, then V lambda star is also finite dimensional irreducible. So, then it must correspond to some dominant weight. Okay. So, what is the dominant weight, you have to think about it. Okay. So, this is where you need to actually have this longest Weyl group element. So, that comes from this Sn plus 1. So, this is something you can do, this is just a computation. So, now let us actually focus on this Verma module and then try to understand what is the character of the Verma module, because that is going to play bigger role in the proof of Weyl character formula. So, let us focus on the Verma module. So, let us call m of lambda. Okay. So, lambda is let us say fixed element, and m of lambda is the Verma module associated with the lambda. So, recall by definition m of lambda is defined to be, you take UG modulo the two sided ideal generated by this h minus lambda of h1, where h comes from h, and x where x comes from n plus. So, in particularly m of lambda is indeed generated by this small v lambda, where h v lambda is given by lambda of h v lambda, and x v lambda is killed for all x in n plus. This is for all h in h star. So, these things we have already realized. So, now I will leave it as exercise. This is not very hard exercise if we use PBW theorem. So, using PBW theorem we can establish very nice basis for m of lambda. So, m of lambda is indeed generated by v lambda as a un minus module, and as a vector space it is naturally isomorphic to un minus as a C vector space. So, in particularly the following is the basis of m of lambda. So, we fix again the order of ordered positive roots. Then if you fix the ordered positive roots, then you can easily see that this m of lambda has the following basis. So, y beta 1 power some r 1 etc., y beta n power r n applied on v lambda, where r 1 etc., r n they are all non-negative integers. Okay. So, this is the basis of m lambda that comes from this highest weight vector v lambda by applying this y betas on which. So, this is the PBW type basis. Okay. So, this we call it PBW type basis. So, note that the weight of this basis element, the h weight of this basis element y beta 1 power r 1 etcetera y beta n power r n v lambda. So, this is nothing but lambda minus r 1 beta 1 plus etcetera plus r n beta n. Okay. So, this is the weight. So, now if we just work it out using this basis, the character of m of lambda is going to be summation. Now, for each basis element you want to have the corresponding exponential. So, then this is going to be e power lambda minus r 1 beta 1 plus etcetera plus r n beta n, where r 1 etcetera r n they all runs over 0 to infinity. So, now this can be rewritten as follows. Okay. So, if you rewrite this, you can write it as e power lambda summation e power minus beta 1 power r 1 times etcetera times e power minus beta n power r n, and this r 1 etcetera r n they runs over 0 to infinity. So, now if you think about it, so what is 1 divided by 1 minus x? That is nothing but summation x power k range from 0 to infinity. So, everything that we are doing in the formal world, so we do not care about the convergence, we just use this formal identity to replace all these things. So, then the character of m of lambda becomes e power lambda times summation e power minus beta 1 power this r 1 range from 0 to infinity times etcetera times summation e power minus beta n power r n range from 0 to infinity. So, now using this identity, if you replace this, then you can easily see that this is e power lambda 1 divided by 1 minus e power minus beta 1 times etcetera times 1 divided by 1 minus e power minus beta n. So, indeed the character using this language, the character of m of lambda has this following closed formula: e power lambda divided by product 1 minus e power alpha, alpha comes from delta plus. So, we have very nice closed formula for the character of m of lambda using this basis of this PBW basis that comes from un minus. Okay. This is indeed a very nice formula, and this is somewhat closed formula for the character of m of lambda. So, such closed formula we want to actually kind of get it in the get it for the finite dimensional irreducible representations as well. So, that is the goal that we are actually proceeding with. So, I will actually leave it as exercise. So, because everything I have done here as the formal computation. So, here is the important question that actually arises. So, we have indeed replaced this summation. So, we have replaced this summation by this 1 divided by 1 minus e power minus beta 1. So, this actually kind of arises the question. So, whether this 1 minus e power minus beta 1 has inverse inside our ring R, okay, and it is indeed the case, and the inverse being this summation. Okay. So, this is something I will leave it to you to check. So, if I take this 1 minus e power minus alpha inside our ring, okay, which is there because this is just a finite sum, and minus alpha is an element of H star. So, 1 minus e power minus alpha is there in the ring. So, the inverse of this 1 minus e power alpha is nothing but summation e power minus r alpha r range from 0 to infinity. Note that this is also there in our ring, okay, because so this is all indeed bounded by the support of this is there inside S of 0, okay. S of 0 contains, so S of 0 contains all this r alpha, okay, r ranging from, okay, the minus r alpha or coming from Z plus. So, that is obvious. So, in particular these are all elements of R, and if you take this 1 minus e power minus alpha, the inverse of that is exactly this. Now, this product is finite product. Once you have inverse for each element, then you can take the product of the inverses, not a problem. So, that is what this product means. And if you take that inverse and then multiply by e power lambda, then you are getting this character m lambda. So, you are giving meaning for all the formal computation, that is all. So, you have defined this bigger character ring in which you can do all the formal computations without any worry. Okay. So, indeed one will be able to do little bit of calculus also. Okay. So, for example, one can take logarithm, one can take exponential and so on in the formal world. So, the way you want to think about it, okay, as long as you have the convergence in the very small neighborhood, okay. So, let us say it is either you can think it as a real variable or complex variables, it does not matter, even the multivariable thing, okay, as long as you can find a very small neighborhood in which the convergence happens, then you will be able to do the calculus, not a problem. So, because the calculus can be done in that small neighborhood, so in particularly you can do the formal computations without any worry. So, that is a kind of like a philosophy behind this formal computations. So, like I said, in particular you can do logarithm, exponential, sine, cos, whatever the trigonometry series or the series that you know from calculus, you will be able to actually do it here in the formal world as well. Okay. So, now we want to actually rewrite this particular character of this m of lambda. So, the way we want to rewrite, using this what is called the Weyl vector. Okay. So, let us define this Weyl vector. So, in terms of the fundamental weights, the Weyl vector is defined to be the sum of the fundamental weights omega 1 plus etcetera omega n. So, recall what are the fundamental weights? The fundamental weights defined to be omega I of h j is given by delta I j. Okay. So, that is how we have defined the fundamental weights. So, now if we take any weight in the weight lattice, that will be written as Z linear combination of fundamental weights. So, that is something we have already seen. The weight lattice being defined to be those lambda in h star such that lambda of h I being integer for all I ranging from 1 to n. Then using the fundamental weights, one can see that this is Z span of omega i's I range from 1 to n. Okay. If you have not done this exercise, you should do. So, now you have this particular element rho inside your weight lattice. So, that is called the Weyl vector. What is special about this Weyl vector? So, if I apply this simple reflection S I of rho, then this is just rho of h I alpha I. Then if you think about it, rho of h I is nothing but summation omega j of h I. Omega j of h I is delta I j. So, this is exactly 1. Whenever j equal to I, you get 1. So, then SI of rho is nothing but rho minus alpha I. So, this is the important observation. Now, one can actually use this observation to prove that. So, here is a small lemma, rho has this following very explicit expression in terms of the positive roots. If I take rho to be omega 1 plus etcetera omega n, then this is exactly of sum of all the positive roots. Okay. So, to prove this, we need to actually use the Weyl group action on the set of positive roots and then see what we are going to get. Okay. So, to prove this, we need this following additional lemma, which is indeed small exercise. For I from 1 to n, we have SI of delta plus difference alpha I is exactly delta plus difference alpha I, and SI of alpha I is minus alpha I. So, what this lemma says, except alpha I, all the positive roots will be mapped to positive roots by SI, and alpha I will be mapped to minus alpha I. So, that is obvious, and this is very simple. So, you write alpha I as epsilon I minus epsilon I plus 1, and then the roots, positive roots are defined to be delta plus in terms of epsilon I basis, it is epsilon k minus epsilon L, where 1 less than or equal to k less than L less than or equal to n plus 1. So, now you just simply calculate SI of epsilon k minus epsilon L, and you can see that this will be exactly epsilon k minus epsilon L if k L both are actually disjoint from I and I plus L, I plus 1. Okay. And if something matches, then what will happen? So, SI of epsilon I minus epsilon I plus 1, it is easy to see, this is minus epsilon I plus 1. So, that is also easy to see. So, now if you actually look at what happens to this epsilon I minus epsilon L. So, let me just write it down here, epsilon I of epsilon I minus epsilon L. So, this is going to be whenever L is greater than I plus 1, okay, for we have this is epsilon I plus 1 minus epsilon. So, this is again going to be a positive root. Similarly, when k equal to I plus 1 and L is greater than or equal to I plus 2, obviously, we have SI of epsilon I minus epsilon L is equal to epsilon I minus epsilon I plus 1 minus epsilon I equal to epsilon I minus epsilon L. So, this is again inside delta plus. So, this calculation simply says that these positive roots other than alpha I will be mapped to positive roots and alpha I will be mapped to minus alpha I. Okay. So, now to prove this identity, you write the right hand side in terms of actually omega i's. Okay. So, to prove the first lemma, to prove rho equal to summation alpha of time alpha in delta plus. So, maybe call rho dash to be the right hand side summation of times all positive roots. So, now you can easily see that this is going to be in the weight lattice. Okay. So, this will be written as some C 1 omega 1 plus etcetera C n omega n. So, that is for sure with C I is coming from Q, okay, because everything is integral. So, when you invert, you can only actually get this rational coefficients, you do not need to go beyond that. So, then it is easy to see SI of rho dash is going to be, so rho dash minus I would say C I alpha I, because S I will fix all the omega j's. So, S I of omega j will be fixed for all j not equal to I, and S I of omega I is nothing but rho minus alpha I. So, this S I of rho dash is going to be just rho dash minus C I alpha I. So, now if we use this S I maps delta plus difference alpha I to delta plus different alpha I, and S I of alpha I being minus alpha I, then you can see that S I of times summation alpha and delta plus is going to be exactly equal to. So, first you just write it as a two different sum. The first sum will be invariant. So, this is going to be summation alpha coming from delta plus minus alpha I, because it is going to just permute it there. Then plus you will have this alpha I which is mapped to minus alpha I. So, of times you will have minus alpha I. Okay, this off we should forget, then only this symmetry will be there. So, forget the off. So, this is what you get, okay, because S I of delta plus difference alpha I maps bijectively to delta plus difference alpha I. So, that summation will be preserved, and then only thing that is mapped alpha I to minus alpha is written here. So, now if you use this, then what you get? You can easily see that S I of rho dash is going to be rho dash minus alpha I. Okay. So, I will leave it to check this. So, now with this you can see that rho dash minus C I alpha I is equal to rho dash minus alpha I. So, that implies C I equal to 1, and this is true for all I. So, if you go back to our rho dash expression, you can see that forces that this is exactly equal to rho. So, rho dash equal to rho. So, this proves that when you take this Weyl vector, so this can be written as off sum of these positive roots. So, indeed using this one can actually claim the following, so which I will actually prove it later. So, this is called denominator identity. The proof of this will be given in the next class. So, the denominator identity says, so if I take this summation sine of W or sine of sigma e power sigma rho, where sigma runs over the symmetric group, the Weyl group, which is exactly equal to e power rho times product 1 minus e power minus alpha. Alpha comes from delta plus. Okay. So, this is something we will prove later. Okay, I will stop here, and then we will continue in the next class with the proof of this denominator identity, and using this denominator identity we will be able to again rewrite the character of the Verma module, and we will use that expression in order to get the Weyl character formula for finite dimensional irreducible representation. Okay, I will stop here. Thanks.